Okay, so we've got this problem here. Got the shaft. It's got a helical gear and a bevel gear mounted to it. And then two bearings that are supporting it. Both the helical gear and the bevel gear have forces acting upon them, obviously, because what's the point of having gears otherwise? And of the supports are each going to have reactions as well. So the gear at A is the one that takes any of the thrust that's left over, whereas C here is only going to be acting in the Y and Z directions. So, and made of that particular steel, and got fillets with a certain radius, and then surfaces are finished by grinding. So we're going to start off by drawing solving for the various reactions, drawing our torsion, our axial load, our shear, and our bending moment diagrams for the shaft in the planes in question. So here's just a little sketch showing our gear, showing our shaft with the gears and the various forces that are acting upon it. So one thing to note is that these, so BZ, it's supposed to be a Z there. BZ and BX here are functions of this BY. And we're given the values for the forces on the bevel gear. So when you look at this, you'll notice that basically when we take a moment about the x-axis, there's only two of these forces that essentially end up in that equation, because all the other forces are either acting in the x-axis or they're acting or their line of action passes through the x-axis. So the only two forces that you end up left with are By and this dz here. So I just drew a quick kind of side view of the gear here. So the smaller bevel gear, and then the bigger helical gear. And then just showing those two forces. So again, just taking the sum of the moment about x will allow us to find what By is. So sum of the moment about x is equal to 0. So the 5.33 kilonewtons times the 187.5 millimeters. Yeah, one thing that was specified is that kind of the points where the forces act. And on the helical gear, they're kind of all acting on the outside there, which is fairly obvious. So that's acting. It's got a 500 millimeter diameter, so it's acting at a 250 millimeter radius. And then for the bevel gear, they're acting like kind of at a point on the bevel gear, at kind of the 375 millimeter diameter mark, or again at 187.5 millimeters in radius. So taking our moments, we're able to solve for By is equal to 4 kilonewtons. And then from that, since we're given Bx and Bz in terms of By, we can solve for Bx as a negative 0.05 kilonewtons and Bz as a negative 1.47 kilonewtons. And that's just I assigned the signs just based upon kind of their directions on this graph relative to the coordinate system chosen. So for solving some unknowns, I'm going to start off with a free body diagram of the xy plane. So I'm going to be omitting any forces that are acting in the z direction for this one. So again, when we're kind of looking at it from the side, the way that the forces on the bevel gear, the helical gear, that's the helical gear, is situated is that they're both of those forces are kind of are acting kind of in the center here, whereas when we look at our bevel gear, they're acting kind of like on the top corner, so they're a bit offset there. So at this point, we can solve for what AX is just by taking the sum of the forces in the x direction, because there's only, there's the two other known forces that correspond to that. So that is, 0, sum of those forces, so 0 is equal to x minus the 1.05 kilonewtons minus the 0.37 kilonewtons. So minus the x component of the force on the bevel gear and minus the x component of the force on the helical gear, because both of those are acting in the negative x direction. So that reaction there ends up being 2.42 kilonewtons. Then we can take a moment. We can go ahead and take a moment about the z-axis at point A. So there. So again, the forces that would show up there are the 4 kilonewtons from the helical gear, and then both of the 1.37 kilonewton forces from the bevel gear. Both the y direction and the x directions ones would show up there, just with different moment arms. So and cy is our unknown there. So solving for that, relatively straightforward. Cy ends up being negative 0.539 kilonewtons. And then once we have that, we can solve for what AY is just by doing the sum of the forces in the y direction. So again, that's fairly straightforward. So AY ends up being a negative 2.091 kilonewtons. So these are both the reactions are going to be both of those reactions are going to be vertical reactions in the pushing downwards on the shaft. And then next up, move on to the XZ plane. So again, I'm just going to be omitting any forces in the y direction on this graph. So at this point, we've got our unknowns of AZ, CZ. So we can solve, same idea, we can solve for what CZ is by taking a moment about the y-axis at A. So again, relatively straightforward. The forces that will show up are the Z component of the force on D, on our bevel gear, and both the X and the Z forces acting upon our helical gear at B. So relatively straightforward. We can solve for CZ as being negative 6.916 kilonewtons. So again, it's actually acting in this direction based upon the fact that we have our, again, our coordinate system is based upon that there, because we're keeping with the right-hand rule. Then next up, we can solve for what our AZ is. So some of the forces in the Z direction can do that. So that ends up being a 3.052 kilonewtons. And then we can move on to graphing. So basically, kind of we're starting with the x-axis at the point where the starting with our x-axis at the origin here. Sorry, at A. And again, I'm defining the coordinate system this way so that we're keeping with the right-hand rule. One thing you'll note is that this graph did not keep with the right-hand rule. So I had x. Well, I guess it specifies the x-axis is this axis. I suppose it doesn't specify per se that it's increasing in that direction, although I think that would be the general assumption. But anyways, if we want to be keeping with a right-hand coordinate system, then we need to be having x increase in this direction, y increase in this direction, and z increase in this direction, which is what I had laid out. Why doesn't it let me? No, let me select the damn. I don't know why it's not letting. This is quite irksome. Yeah, what I had laid out there. So, relatively straightforward. We're just, so our axial only has the three forces in the x direction. So starting out with the reaction at A, and then it's reduced a bit at B. Sorry, it's reduced a bit not at B, but you'll notice like when you look at this shaft here, there's this thick section of the shaft here, and then kind of this gear here kind of fits onto here. So the idea is that you're going to get some sort of axial force pushing on the gear at B, and it's not the keyway itself that is necessarily going to be holding, carrying that axial force, because the point of a keyway is that you're still able to kind of slide the gear onto the keyway. The keyway is there for transmission of torque primarily, not necessarily for it's not a press fit kind of holding it on there. So the keyway isn't what's holding that axial force. It's actually going to be kind of held by this shoulder here at this shoulder here at E. So yeah, our axial force here. So I had amended that on the graph, but I forgot to change the location. So this 550 here is B, the location of B. This will actually be 400 millimeters there. So yeah, we're here, gets dropped down, stays like that the entire way until we get to the very end. Our torque's just the torque's constant between B and D, between our helical gear and our bevel gear. So, and value that's 1,000 Newton meters. And then our shear looks like this. Shear in the Y direction, which leads to a bending moment about the Z-axis diagram. Now again, just keeping in mind that our shear diagram integrated over the length gives us our bending moment diagram. In this instance, it doesn't reach 0 at the very end, and it doesn't reach 0 at the very end because of the fact that we have at the very end here, we have this force here, which again, when I'm looking at it straight on, it's basically an external bending moment applied at the very end of the shaft. So we still got that force there that is causing a bending moment. That means that we're not going to be dropping down to 0 at the end there. But we hit our maximum magnitude of the bending moment at B, at our helical gear. And for the shear in the Z direction, looks like this. Relatively straightforward to construct that. And again, bending moment diagram integrated gives us our our shear moment diagram integrated gives us our bending moment diagram, with the caveat that again, any external moments that are applied cause jumps. So again, that'll be caused right here due to the fact that we have this little force here that's going to be causing that'll be basically causing external bending moment based upon its magnitude and the 250 millimeters between there. So the maximum bending moment caused on the shaft in the Y direction, caused on the shaft about the Y-axis is at C, at the bearing that's between the two gears, and the magnitude of that is 2,132 kilonewton millimeters. So at that point, basically, we've got a bending moment about the x-axis and about the y-axis as well. So basically, there's going to be kind of a certain orientation where we have a maximum bending moment, and the magnitude of that is just going to be equal to that. So just the square of those two, add them together, and take the square root. Because again, Pythagoras' theorem works. We don't necessarily need to know the for these purposes, we don't necessarily need to know kind of the exact orientation of that. It's not strictly necessary, I'd say, to do that. We're more so worried about how to say this. Yeah, we're worried about what the magnitude is, because the magnitude is what causes the stress, and the stress causes cracking. The cracking is not necessarily, we're rotating the shaft. We're rotating the shaft around, and the point where the maximum stress occurs is kind of a point in space. So as we rotate the shaft around, points of the points on the shaft are kind of going up and down to that amount. So the stress that's occurring due to this is completely fluctuating. So it's not like the fact that we have the maximum stress at a particular point in space doesn't really tell us anything about the shaft itself, so we don't really care. So as for the calculations, next step that they want us to do is the fact that we want to figure out what the kind of equivalent bending stresses are for at B, C, and E. So B is the point where the helical gear is, C is the support between the helical gear and the bevel gear, and E is just at the shoulder where the helical gear is kind of pressing against. So for this assumption, again, we're gonna be neglecting the direct shear. It usually doesn't cause much, especially considering at the points where the bending moment's the highest. Typically speaking, the direct shear is either minimal or zero. But we do know that at B we have the three types of loads. So we have the axial load, we've got the torsional load, and we've got the bending load. So the bending, again, is fully reversed. So it is fluctuating up and down. It is going from a maximum amount to a minimum amount. The only thing that the sign changes, the magnitude of that is the same. So the axial and torsion, however, that's constant. The question also gave us information about the stress concentration factors at the keyway. So Kf there is going to be equal to 1.6 for the bending and torsion, and 1.0 for the axial. The other thing that they did mention is that at the keyway we can use a CS is equal to 1. And that'll come into play for the next step when we're kind of calculating the safety factor. But anyways, so we've got the axial. So the stress, the axial stress, again, that's just the load divided by the area. So that'll be negative 0.3 megapascals once we round it to a reasonable value. Again, reminder, the KF there was 1.0, so I just didn't include it because it's 1. Wouldn't hurt to put it in there and say it's 1.0, but if it's 1, I often just don't bother putting it down there. Torsion, however, so the torsion at B, 16 T KF time divided by pi d to the third. So plugging the values in there, 16 times 1,000 Newton meters times 1,000 millimeters per meter times 1.6 divided by pi times 80 millimeters to the third. That gives us 15.9 megapascals. So again, both the axial and the torsion are mean stress. Contribute towards the mean stress because those are constant. They're not varying. So we can plug that into our mean stress equivalent formula. So again, and the formula that I had given you guys in the slides included the KTs in this formula. So again, I'd already included it kind of in this calculation, above, so you don't need to do that. So anyways, that's just negative 0.3 divided by 2 plus the square root of the 15.9 squared plus the negative 0.3 divided by 2 squared. Obviously, the negative goes away when you square it. So that ends up being 15.7 megapascals. So the fact that we have basically the compressive axial stress will reduce the mean stress somewhat from the amount that we basically would have been caused as the equivalent from the torsion. Doesn't completely get rid of it, but it knocks it down a little bit. And then we got the bending, kf times 32m divided by pi d to the third. So again, our m value at that point, we just calculate based upon taking the square root of the squares of the m's about the y and z axes at that point. So that'll be 1150 and 1679. So the maximum magnitude, at a particular orientation of the moment there is 2035 kilonewton millimeters. So finding out what the stress is, 1.6 for our kf times 32 times 2000, 20, 30, 35 times 1,000. I threw the extra digits in there for the 1,000 just to convert it from kilonewton millimeters to newton millimeters, and then divided by pi times 30 millimeters to the third. So units all cancel out to be newtons per millimeter, so we're at megapascals. Sorry, newtons per millimeter squared. So we're at megapascals. So that'll be 64.8 megapascals is our bending stress, and that's also the only thing that contributes to our amplitude, to our variation. So that's our SAEB, our stress and amplitude at B. And then we got C. So there's no stress concentration going on at C. It's it's a smooth shaft in a bearing at that point. So there's nothing there that would be causing any stress concentration. So at that point, torsional stress is the same as at B, just without the KF. So I'm gonna, just take that value, divide by the 1.6. That gives us 9.9 megapascals. Axial stress is the exact same as B because there was no KF applied at B as well. So take those values and plug them into the equivalent mean stress formula, and that gives us 9.8 megapascals. Next, again, find our maximum moment at C. Based upon that there, we're at 2151 kilonewton millimeters. So finding our bending stress caused by that, 32 times our m divided by pi d to the third. Again, kf's 1 at that point, so that ends up being 42.8 megapascals. So that is our SAE at C as well. And then we got at E. So at E, the torsion's 0, and the axial load is the negative 2.42 kilonewtons. And the bending stress can be found basically by, if we go up to here to our bending moment diagram. Again, we're kind of just interpolating what goes on there. What goes on here at 400, because it's linear between 0 and 550. And same deal here, also linear between 0 and 550. So just take those values at 550 and multiply them by 400 over 550, and that'll give us kind of the values we can plug into there. So we could either kind of use that to punch it into this equation, or realistically we could just take the bending moment that we solved for at B, which was the 2035, and multiply that by 400 over 550, because both of those things are scaling up. Both of the things that went into there are scaling up linearly, so the total stress will be scaling up linearly as well. But anyways, so we're getting 1480 kilonewton millimeters there. But we weren't, unlike for the keyway, we weren't given our KT, so we need to figure out what that is. What we do know is that the shoulder fillet there has a radius of 5 millimeters. So our big D over little d is going to be 120 over 80. So that's 1.5. And then our R over little d is 5 over 80. So that's 0.0625. And then basically we're just going to our charts in juveniles. So figure 4.35 gives us what our KTs are. So our axial KT, it's roughly 1.95, and then our bending KT is about 1.90. But again, those are our KTs. We need to use our notch sensitivity factor in order to figure out what our KFs are. So based upon interpolation from figure 8.25 of juveniles, looking at that, I was figuring we're looking at probably about 0.92. So I'm gonna pull that up actually here. Yeah, but just want to give me 1 second here. Okay, so yeah, our notch sensitivity. Oh, that's let me think here. Stress concentration. There we go. So looking at this, so this is the graph that we got here. So again, we are looking at a notch whose radius is fairly high here. So our radius would be off the chart over here somewhere. You can kind of see as we get up in the lines are mostly going flat. So at that point, we're kind of just basically kind of also going to need to interpolate between these two lines, the top line and the second one down. So essentially taking our ultimate strength of the material, which was given, that was 1069 megapascals. In KSI, that ends up being 155. So for a 155, we're a bit above the 140 line. Not, not certainly not. It's not halfway to the 200 line. So I kind of figured that zooming in there, probably about there seems reasonable. So maybe a bit less. So anyways, I kind of eyeballed it and said that about a 1.92 seemed reasonable for that. So anyways, using that we're able to solve for our KFs. So that gives us a KF for the axial of 1.88, and a KF for the bending of 1.83. So the axial, again, our load times the KF divided by our area. That gives us negative 0.9 megapascals. So that's the only thing that contributes to our mean stress. So that is our SME equivalent. The bending, on the other hand, so the bending, it's KT times 32 times m divided by pi d to the third. So 1.83 times 32 times 1480 times 1,000 Newton millimeters divided by pi times 80 millimeters to the third. That gives us 53.9 megapascals. So again, that's the only thing that's contributing to our whatchamacallit. It's the only thing that's contributing to our amplitude going on there. So that is our SAE at E, our stress amplitude equivalent. So next up, figuring out where the what the strengths, safety factors are. So we need to figure out what our SNs are. So we've got, we know that SN in general is our SN prime times CL times CG times CS times CR. There's a CT there sometimes too. Again, for the purposes of this course, we're not worried about temperature at this time being, but keep in mind that elevated temperatures can knock down your fatigue strength. But taken from table 8.1 of juveniles, we find that CL is 1, CG is 0.8 for that size of a shaft. Again, your CG goes down as the shaft gets bigger. Got our CR. So they were asking for a 99% reliability. So only 1% of the parts are expected to be able to fail below the value that we're, below the value specified. So that's 0.814. Our SN here, it's steel. So our SN prime, is going to be half of our SU. So that'll be, again, 1069 megapascals divided by 2 gives us 534.5 megapascals. And then our CS, we need to take, again, we need to go back to juveniles, figure 8.73. So, wait, no, not 8.73, 8.13. So that's this one. That's this one here. So as specified, the ultimate strength that we're looking at is 155. So just moving that up here, and it was specified that these were ground. So fine ground or commercially, look at the fine ground and commercially polished line. So at that strength level, it's still 0.9. Hasn't started dropping off yet. So jam all those things together and we get 313 megapascals. That'll be for E and C. Like I mentioned before, the keyway, it was specified that for the keyway we could use a CS of 1. So that basically means that we need to kind of recalculate the SN that we're using. So that SN results in an SN of 348 for the whatchamacallit, for B, for the place on the shaft where the helical gear is mounted. So we can graph our Goodman's diagram here. I'm going to try to fit this to the screen a bit better. There we go. So again, our alternate Goodman's diagram is a line from SY to SY, a line from SN to SU, and then the line from SY to negative SY, and then basically a horizontal line from SN until it intersects there. So this entire area that I'm kind of hatching here, that is areas where we don't expect failure. And then we'll just basically have two different lines for the SN-SU curve line for B and then E and C. So I did that. I also kind of plotted the locations of the two. And I guess the vertical line I drew for the axes kind of didn't show up in my scan, so let's kind of get that. Let's get that on there. Oh, come on, let me select. There we go. So yeah, that's right there. So E is lying in this quadrant. B and C are both in this quadrant. So basically, because E has a mean compressive strength, a mean compressive stress, its failure criteria is based upon this line and not this line at all, right? So for E, essentially what we need is just the safety factor is just going to be the SN divided by the SAE. So that'll be the 313 divided by the 53.9 megapascals. So that gives us 5.8. For B and C, however, we need to use the slightly longer formula that takes into account the kind of the intersection between the lines in question. So again, that's the one that looks like that's the one that's SAE over SN plus R SME over SU is equal to 1 over a factor of safety. So that plugged into here. So at B, our SME is 15.7, our SU is 1,069, and the SAE is 64.8, and our SN for B is the 347. That gives us the inverse of our safety factor. So that's leading to a safety factor of 4.96. C, on the other hand, 9.8 divided by the 1,000 69 plus 42.8 divided by the 313 is equal to 1 over a safety factor. So that leads to a safety factor of 6.85. So the location where we have the lowest safety factor, so that's basically our of the points that we considered, that's where we expect the failure to happen before anywhere else, is at B. But it's still got a safety factor of 4.96, so that's that's fairly high for a lot of applications. That'll be certainly quite suitable. And yeah, that's about that.